we have seen how to perform the basic operations on continuous time signals, and from this lecture we will begin understanding how to perform the basic operations on discrete time signals. And the first operation we are going to understand is time shifting operation. We have a fairly good idea of how to perform the time shifting operation on continuous time signals, and the concept will remain same in this case as well. So to understand the time shifting operation on discrete time signals, you must have the knowledge of time shifting operation on continuous time signals. And now we will begin our discussion with one example discrete time signal, which is xn. You can see that xn is a discrete time signal having value equal to 2 when n is equal to 0. It is equal to 1 when n is equal to 1. It is equal to 3 when n is equal to 2. It is equal to 0 when n is equal to 3. It is equal to 0 again when n is equal to 4. Similarly, up to plus infinity, it is equal to 0. Now moving on to the left hand side, you can see that it is equal to 3 when n is equal to minus 1, equal to 2 when n is equal to minus 2, equal to 0 when n is equal to minus 3. Similarly, it will be 0 up to minus infinity. Now looking at this waveform, it is clear that drawing this waveform every time is not at all required. Why? Because here we are simply writing down the values of xn for the corresponding integer values for the corresponding values of n. Therefore, the waveform of a discrete time signal is different than the waveform of a continuous time signal. In case of continuous time signals, we have a continuous variation of signal with change in time. But here in this case, we only have the values of signal for the discrete intervals of time. So there is no need of the waveform to analyze this signal. We just need the values of signal corresponding to the different values of n. For example, here in this case, at minus infinity, xn is equal to 0. At minus infinity, it is equal to 0. Similarly, it is 0 up to minus 3. Then it is equal to 2, 3, 2, 1, 3. 2, 3, 2, 1, 3. Again it is equal to 0 when n is equal to 3, and remains 0 till n equal to plus infinity. Usually we don't write these 0 values. We write the values starting from the non-zero value to the non-zero value. Therefore, we will write xn as 2, 3, 2, 1, 3. 2, 3, 2, 1, 3. Now it is very confusing. We don't know for what values of n we are having these values, and therefore we simply put one arrow mark below the value of xn, which is corresponding to n equal to 0. Here you can see that xn is equal to 2 when n is equal to 0. Therefore, we will put one arrow mark below 2. This indicates 2 is the value of xn when n is equal to 0. And therefore, this 1 will become the value of xn when n is equal to 1. Therefore, this 3 will become the value of xn when n is equal to 2. Similarly, this 3 will become the value of xn when n is equal to minus 1, and this 2 will be the value of xn when n is equal to minus 2. The same thing we are having in this waveform as well. So using this representation for discrete time signals, we can easily perform the analysis, and we will use this representation a lot in this course. Now we will move back to time shifting, and we know there are two types of time shiftings. The first one is right shifting and the second one is left shifting, and we will first understand we will first understand the case of right shifting, and we know what will happen in case of right shifting. For example, let's say there is a continuous time signal xt, and we perform the right shifting by 1 units. So let's perform the right shifting by 1 units. This means t0 is equal to 1, and when there is right shifting, we will have negative sign between t and t0. t0 is equal to 1, so we will have xt minus 1. So the whole waveform of xt will shift towards the right by 1 units. And there is important thing to notice, which is the sign. We will have negative sign. Initially this thing is confusing, but we have seen some examples in the basic lectures, and there I have made clear why we have negative sign when there is right shifting. So in case of discrete time signals, we have signal xn, and xn is equal to this 2, 3, 2, 1, 3. 2 is at the origin, and we are performing the right shifting by 1 integer value. This means we will have the new signal xn minus 1. So this whole waveform will shift towards the right by 1 integer place. As you can see, this is the waveform of signal xn minus 1. And now you can notice one thing, that xn minus 1 is equal to 3 when n is equal to 0. So values will remain same, 2, 3, 2, 1, 3. I'm talking about this representation. The value will remain same. So we have 2, 3, 2, 1, 3. But these values are for different values of n. Here we have xn equal to 2 when n is equal to 0. But in this case, we have xn minus 1 equal to 3 when n is equal to 0. Therefore, we will put arrow mark below 3. The whole signal waveform will be shifted towards the right because of this arrow shifting towards the left. Here you can see the arrow is here, and now it is shifted to this position. So when this signal waveform is shifting towards the right, we are calling it right shifting, but the arrow in the representation is shifting towards the left, and everything is very easy to understand. So this is all for the right shifting. Now we will move on to the next type of shifting, which is left shifting. Left shifting is the case when the signal will shift towards the left, and this will happen when you replace the independent variable by t plus t0. So here t0 is positive, and we have a plus sign between t and t0. In this scenario, the waveform will shift towards the left by t0. For example, let's say t0 is equal to 2. So we have xt shifting towards the left by 2 units, giving us a new signal xt plus 2. But we are discussing the discrete time signals, therefore we will talk about xn plus 2. And like previous case, we will first write down the values of xn: 2, 3, 2, 1, 3. xn is having value equal to 2 when n is equal to 0, but after performing the left shifting by 2 integer values, this arrow will jump here and then jump here. So we will have the arrow placed below 3, and the waveform will look like this. This whole waveform is shifted towards the left by 2 integer places, and therefore 3 is now located at n equal to 0. This is the waveform of xn plus 2. So I hope whole process is clear to you. You now understand how to represent discrete time signals, what is the meaning of this arrow, and how to perform right shifting and left shifting on a discrete time signal. So this is all for this lecture. I will end it here. See you in the next one.